Hello, everybody, and welcome back to another episode of Dome to Home. As always, my name is Jeremy. I'm a navigator at Fiske. I also do some presenting, and I've been working with you guys all on these Dome to Homes. With me, we've got my friend Tara again. Hey, Tara.
Hello. Hey, Jeremy. Yeah, again, I'm Tara. I'm a planetary scientist and a CU alum and a couple other thing presenter and outreach coordinator and all sorts of fun stuff here at Fiske. But today I am here to help walk you through this awesome topic of exoplanets. So we've been doing exoplanets for a couple weeks now. We've got even another week of it. But today in particular, we're going to be talking about how we find all of these exoplanets, which is a crazy, crazy thing. So before we get started, just the usual stuff. If you're having trouble seeing the screen at any point, go ahead and maximize your screen, go full screen with that video. That'll help you really see some of these stars and cool things in the pictures we have to show you. Also, if you have questions at any point during the show, you can drop those into the chat here on YouTube. Our friend Emily is behind the scenes and she's keeping an eye on those. You can also use the link that's posted. It should be pinned at the top of the chat or it's down in the description of the episode there. If you're having trouble using the YouTube chat, go to use that link. That'll take you to a Google form. You can put your question in there and that'll populate to us here so we can get to that. So we'll try to answer some as we go through the episode today, but we're also going to have time at the end dedicated just to questions. And I saw our form had a ton of questions. Talk a little bit about them. Now, the first one we're going to talk about is direct imaging, which is basically just taking a picture of an exoplanet. This may sound like a really difficult thing to do because it is. It is very, very hard to do. And so we've only found about 27 different exoplanets out in the world using this direct imaging technique. It's really, really hard because planets are super, super small compared to stars, right? I mean, even here in our solar system, our biggest planet, Jupiter, you could put 30 Earths inside of Jupiter. It's still 1,000 times smaller than our sun. And so exoplanets being so much harder to find or to see compared to the stars, we have to use different techniques. And you might be thinking, well, we've got all these crazy telescopes like Hubble. Why can't Hubble see all of these exoplanets going around? Well, Hubble is really good at taking pictures of things that are really big and really far away. So you've probably seen lots of pictures of galaxies and supernovas and things like that. There's always the famous one that we like to show of the Crab Nebula, which is the remnants of a supernova. This is a picture that Hubble took. But this thing is 6,500 light years away, and it's several hundred light years across. So it's massive, massive, massive. We can compare that to a picture that the Hubble Space Telescope took of Pluto right here in our own solar system. A small object, but not terribly small. But that's as good as it could do. So taking pictures of planets, even far away planets, is not what Hubble is made for. Instead, what we do is use a different technique, not visual light like the light we see with our eyes, but we use infrared light. So what we can do, infrared light is really good at heat. It kind of tells us how much heat a planet is hanging on to. So even if we can't see the planet going around the star, we can use infrared to kind of block out the star and just see those planets as they're going around, which is what you see here. Those really bright little dots are the planets looking in infrared light. Here's another great one. It's a little video. I like it a lot. As it's going around there, you can see all of the little dots going around. They've blocked out the star there in the center, but we can see the planets going around it. So this works really well for planets that are pretty big or really far from their stars. That makes it a lot easier for us to find. But again, we've only found about 27 using this method, so it's not terribly effective, but it does a decent job. Now, the second one we're going to talk about is gravitational lensing. That may sound like a big, scary thing, but it's actually not terribly complicated. Now, this is another one. We've only found about 30 planets with this method, but in theory, it makes a lot of sense. Because the reality is that gravity bends light. Maybe you've heard of this before. So light, moves past things, and gravity can actually affect the way that the light is moving. This is a really popular technique that we use to find black holes in particular, because they don't reflect any light. We can see how they bend the light around themselves. We've got a really great video that shows this really well, and I want to show that for you guys. Now, this is of a black hole, and this is specifically about the black hole that we took a picture of, but this is kind of how we did it. There we go. So you can see that black hole, that source of really strong gravity, is bending the light around it. So you can see the light is coming towards it, it gets bent around. And if we move around to the right orientation here, you can see how that light is appearing to us. So this works really well with black holes. This also works really well with other things that have a lot of gravity, things that are supermassive, like stars. Now, this even kind of works with planets going around stars too. The planets themselves probably don't bend the light quite as much as a star does, but it does cause a little bit of bending. And when you put that with the star, then it ends up bending the light in a way that we could recognize. So we can tell the difference between light being bent around just a star and light being bent around a star and a planet. It's a little bit different. So this is also another way that we find those rogue planets that Rami was talking about last week. Those ones that are out cruising around the universe, not actually orbiting a star, they're just out there by themselves. Of course, planets don't emit any light by themselves, so they'd be dark and hard for us to find. But we can see the way that the gravity around them is acting and changing the light that's moving around them, which is pretty cool. Now, the third method, this is where we start getting into the ones that are actually super effective. The third one is called radial velocity, or it's also sometimes called the Doppler method. Now, we found about 450 different exoplanets using this method. And it comes back to gravity again. We're still talking about gravity. And this time, we're talking more about the way that the gravity interacts between the planet and the star. Because stars, they're really big. Planets aren't nearly as big, but they do exert some gravity. Everything that has mass has gravity, and it affects the things around it. Well, if you've got a good-sized planet that has quite a bit of gravity, as it's orbiting around its star, it's going to pull on the star, and it makes it wobble, as we say. So this is a wobbly star. It's constantly being pulled in different directions by the gravity of the planet that's going around it. So you can see that really well here. Now, normally it doesn't happen quite on this scale. We don't actually see a star going back and forth in space. This is not something that we observe with our eyes. What we can do is look at the spectra of the star. That just means that the light that it's putting out, so different elements in the periodic table reflect light differently. And they have these things called spectra, which is what you see here. These different lines for each element. It's kind of like a fingerprint. Every element and molecule has different lines. But say if we're looking at a hydrogen molecule, it's always going to have those same lines, and they're always going to be in the same place, and that's at the same wavelength. But when we have this radial velocity thing going on, or this Doppler, when the star is being pulled back and forth, it actually changes what we see. We see those lines shifted to different positions, depending on where the star is, if it's moving towards us or if it's moving away from us. It causes those lines to shift a little bit. And so we can look at how those lines are shifting and tell that there is a planet causing that star to wobble back and forth. So when we see it in our data, it just kind of looks like waves, like this. That's what we end up seeing. And that just shows us that that star is moving back and forth. Well, why would a star move back and forth? Because a planet is pulling on it. And again, this works really well for really big planets that have a lot of gravity, especially if they're close to a small star, because they can exert more gravity on that smaller star and pull it back and forth a little bit more. Now, the most effective way that we've used to find exoplanets is called the transit method. Now, we've found 4,000 or so exoplanets with this method. So this is our best method. This is our, I won't say it's the easiest method, but we've also had 2 separate telescopes that have used the transit method to discover exoplanets. And those were called Kepler, which is the one here on the top, and then another brand new one called TESS, which is the Transiting Exoplanet Survey Satellite. And TESS has been up for a little over a year now, I think. So we've been getting some really cool data back from these. So what is the transit method? Well, we've got an excellent demonstration here that we can show you of how this works. Basically, we're looking for planets that pass in front of their stars, kind of like an eclipse. So we watch a star. We can't actually see the planets going around it, but we can measure how much light we receive from the star. So like you see here, as a planet passes in front of that star, it blocks some of the star's light. And so if we're just measuring the light amount, we see a little dip as the planet goes in front of it. And of course, bigger planets make bigger dips because they block more light. Smaller planets make smaller dips. They block less light, but we're still able to detect that little dip. So this is the most effective way that we found to find these exoplanets, which is really, really neat. And again, we've used TESS and Kepler to do this. It does have a limitation. It is really good for really big planets that are really close to their stars because they're going to block the most amount of light. But we also have to be careful for stars that we're looking at its different orientations. So if we were looking at a star system and maybe it had a planet going around it, but if we're looking at it kind of from the top down, like you see in the picture on the left, we're not going to see that planet pass in front of the star. So there's no transit there. We would completely miss that. And any angle that that's going to be at where we don't actually see the planet move in front of the star, it could be tilted at just the right way that we don't see that. So we're really only going to see ones that are at just the right angles. Like you see here on the right, if we're looking at a planetary system, a star and all of its planets kind of edge on like that, then we'll see the planet moving in front of the star. And it can be at, there's a good range of angles that it works for, but definitely not all. So we do have a little bit of what we call observation bias kind of built into all these different methods.
Yeah, and that can be kind of weird to think about because I know if you think about our own solar system, all of the 8 planets are in the same plane more or less, right? So you would think, well, if you were looking out at other planets, why wouldn't you always just see a transit? But we'll show you here in a little bit of where we found some of these planets, and we see them everywhere. So not all of these other systems are just in the same plane that our own solar system is in.
Exactly. That's what you have to remember about space. There's really not any up or down or anything like that. There's no one set direction that planets orbit around their stars. It could be at all different angles because space is just space. It's all there is. So again, we have since found thousands of these exoplanets, and we can show you a cool graph too of all the different ones and the different methods that we found. So you can see there, we've got all of the radial velocity ones are kind of grouped together. That's because that method is really good at finding these planets that are really big and really far from their stars. When it says period there on the bottom, that's just basically a year. How long does it take for that planet to go all the way around its star? So with radial velocity, we have really big planets, really far from their stars. You can see the transit method is really good for really big planets that are close to their stars. They have really short periods. That's another thing we have to remember about transits and exoplanets is they won't confirm an exoplanet from just one transit because it could just be a fluke. I think they usually have to wait for somewhere between 3 and 5 different transits to actually confirm that, yes, okay, this is a planet and it's not something weird that's happening with that star.
Right. It's all about finding patterns. If you saw a dog walked by once or something like that, you wouldn't necessarily expect that that dog was going to walk by your house every day for the next year or something like that. But if you saw that dog walk by your house every day at the same time, the same direction for a year, you could assume that maybe it's a dog that lives in your neighborhood that is, you know, circling around your house or something like that.
He's on a schedule.
Yeah.
He's got things to do.
That's
places
right.
to be.
He's got someone that walks him at the same time every day.
Yes. I like that analogy. That's a really great analogy. So yeah, that's all the different ways that we have found all of these exoplanets. And with the transits in particular, we can show you sort of where all of these are. So the first satellite, Kepler, found tons and tons and tons, again, thousands of exoplanets just on his own. He was up in space for a couple of years. It was actually partly run by students here at the University of Colorado. There were students at LASP that were helping to drive Kepler and make sure he's pointed in the right directions and keeping tabs on things. So you can see all the little colored dots on your screen. This is, again, maximize it if you have trouble seeing it. All the little colored dots there are stars that Kepler looked at and found a planet going around it. At least one planet. Some of them had more than one. Some of them had 2 or 5 or 7, tons of planets. You can see there's one really bright patch right there at the top of the screen there where there's tons and tons of those colored dots. That was towards the end of our time with Kepler, his motor broke and he just stared at the same patch of space for a really long time. But look at all the exoplanets that he found. At that point, we realized that pretty much every star that Kepler looked at had a planet going around it, which is crazy to think about. So Kepler did reach the end of his life just a couple of years ago, and that was when we put up TESS. And TESS looked at much more of the sky. It's a much newer, much better telescope, and again, found thousands more of these exoplanets, which I think is so cool.
Yeah, so now these newer dots, I put on the new dots that represent those planetary systems that TESS has found, and then I've also put in little rings around them so they kind of stand out a little bit more. And I don't know, Tara, did you already say what the colors meant?
I did not.
You did not. So you might notice that all these different colors, there are different colors, those are just a measure of distance. So the red, orange, and yellow colors are actually closer to Earth. The blue, green, and yellow, or blue, green, and purple are the planets that are further away. So you can see some of those TESS planets that have been actually becoming, or excuse me, some of the planets that TESS has been finding are actually a lot closer than some of the planets that Kepler stared at for so long.
And hopefully in the next year or two, we will have an additional telescope, the James Webb Space Telescope, that'll also be able to go up into space and help us find some of these exoplanets, among many, many other things that James Webb is supposed to do for us. We're all really excited about that one too. So I wanted to get through all of those pretty quickly because I know we have a lot of questions that came in on our Google form, and I also wanted to check and see if we had any that came through on the YouTube. I know we did have one exoplanet question that came in. This was from Amelie. I'm so sorry if I mispronounced that. But she asked, how do we know the mass and the distance and the composition of an exoplanet because they're so far away? Which is an excellent question. And it depends on the method that we use to detect this exoplanet as to what we can learn about it. That's another reason why the transit method is so useful, because we can tell how much of that star's light that the planet blocks. So that gives us an idea of how big the planet is. So we can tell that it's a certain size because it blocks a certain amount of light. Now, this is really useful as well for the composition part of your question, because we can use that same technique of spectroscopy of the light showing us different elements. So when a planet moves in front of its star, the star's light is moving past that planet. If it's a gas planet, maybe the light's coming all the way through the planet. If it's not, maybe it's passing through the atmosphere of the planet. And we can read that light that's coming back at us and tell, okay, is it different than what we see from most of the star? Is there some different kinds of elements that are in there that we can see? So that's one of the really useful things about this technique as well, is that we can tell what sort of things are in or around this little planet, which is pretty neat, I think. At distance, we mostly just measure by the distance to the star. We don't always separate that from the distance from its planet. Usually, in the grand scheme of things, these planets are pretty close to their star on like a universal scale. They're usually pretty close in, just kind of like our planets are decently close to our star. But that's just how we do that. So that was an excellent question. I see another one from Gail here. Gail, why exoplanets have colors? Well, exoplanets have colors the same reason that all of our planets have colors. They're made up of different things. They have different kinds of elements, gases, or even metals or things like that. Depending on what a planet is made out of, it's going to look different to us. It's going to have a different color for us. So it's the exact same thing with exoplanets. Exoplanets are just planets. They're just going around a different star, a star that's not ours. And so you can think of them just like the planets here in our solar system, like Jupiter, or like Mars, or something like that. They're going to behave very similarly, at least in the grand scheme of planets, as far as that goes. Do we have any other exoplanet questions? If not, I do have plenty of just general astronomy questions that came in that I do want to address. If nobody has anything about specifically exoplanets right this second, I can go through and start talking about some of these things because they are super cool. So our first question came in from Jose, and Jose wants to know, what is astronomy? Excellent question. Pretty simple. Astronomy is just the study of space and everything that's in it. So that's stars, planets, asteroids, comets, satellites, even the Earth. We use astronomy to study the Earth even, because Earth is a planet. So astronomy is just us studying the universe and all of the different stuff in it. It's a very broad field. Now I have two questions here about galaxies. Giovanni wants to know, what is a galaxy? And then we had a question from Jonathan, what is the closest galaxy? So galaxies are really collections of stars. They're all grouped together. There's usually something really big at the center that has a ton of gravity that holds everything together. But it's just a whole bunch of stars. And sometimes there's gas and dust in there. That's also where, you know, planets and comets and everything, they're just kind of grouped together. You can think of it like if the whole universe was Earth, you could think of a galaxy being kind of like a city. So there's all sorts of smaller things in there, but it's just one collection in a larger group of the universe. So here Jeremy's put up some really cool galaxy pictures for us. That's what some of our galaxies look like. So I'm pretty sure these are probably taken by the Hubble Space Telescope. It's really good at taking pictures of galaxies. The closest one to us is called Andromeda, the Andromeda Galaxy, which is really, really similar to our own galaxy. The galaxy that we live in is called the Milky Way. But the closest one, our next door neighbor, is Andromeda. I say it's our neighbor, but it's 2.5 million light years away. So it's a very distant neighbor, but it's the closest one to us. Galaxies themselves are really, really big. Our galaxy is about 100,000 light years from side to side. And so these are really, really big. There's a lot of space in between them. But this wonderful picture here is Andromeda. That is our closest neighboring galaxy. What else did we have in here? The ever-present question of why is Pluto not a planet? I love this question because I always like to tell people Pluto is still a planet. It's just a different kind of planet. Dwarf planets are still planets. They're just different kind of planet. So the main reason why we reclassified Pluto was because we found a lot of other things in our solar system that were a lot like Pluto. In fact, Pluto was a lot more like these other things than it was like the planets that it was classified with. So, you know, we always talk about Pluto being really small for a planet. It orbits differently than the main planets in our solar system. Jeremy's put up the orbits of our planets here. You can kind of tell when you get to the dwarf planets, they don't orbit the same way. They orbit kind of cockeyed, or sometimes they're completely off. They have very different, very strange orbits. And once we found more and more of these, we realized that Pluto fits in more with this group than he does with the actual, what we call major planets, the 8 big planets. Pluto fits in better with these dwarf planets. So there's 5 of them in our solar system altogether, Pluto included. And Pluto is the biggest of the dwarf planets. He's like the king of the dwarf planets. So I hate to use the term demoted. I don't think we didn't demote Pluto. He was just reclassified. He was just put into a different class with planets that were more like him.
Great question.
Great question. Get that one all the time. Ooh, another good one from Jonathan. Why does the moon always show us the same face? Now, this is something a lot of people don't even realize, that they've only ever seen one side of the moon from here on Earth. It's absolutely true. And think about it. Next time you go outside, go a couple nights in a row and look up at the moon. You're always going to see the same side. Now, it really just comes down to, again, our friend gravity. Gravity kind of is what holds the moon in orbit. But the gravity between the moon and the Earth works out just right to where the same side of the moon is always facing us. The moon is rotating just like the Earth does. So there's still day and night on the moon. There's not one side that's always light and one side that's always dark. It's still rotating, but it's rotating at the same rate that it's orbiting around the Earth. Exactly the same. So we just always see that one side because it's turning at just the right speed, that the same side always ends up pointed at Earth. It's all just down to gravity again. Now, this is actually a really common thing that we find in our solar system. Lots and lots and lots of moons are what we call tidally locked, is how we refer to that. So only one side of them ever faces their planet. We also see this with some planets and stars, especially in these exoplanets. Weird stuff happens then. If you missed out on our Dome to Home last week, they talked a little bit about tidally locked planets. And that's how we end up with things like lava worlds and really strange, crazy stuff. Let's see. Reuben is asking if there might be exoplanets that we don't know about yet. And I would say absolutely. We've found 4,000 and something of these exoplanets, but there's still billions and billions and billions and billions of stars that we have not looked at yet. There's an uncountable number of stars out there. And really, our telescopes are only good enough that we can really only find exoplanets within a small circle around the Earth. I don't think we found any exoplanets around stars in other galaxies. That's just too far away. We've only been able to find ones that are relatively close to us. So there's a whole universe out there full of stars, and pretty much everyone probably has a planet going around it. So there's probably an uncountable number of planets, just like there's an uncountable number of stars. It's really fun to think about. I like that question.
Yeah, I have a picture I want to bring up that kind of goes along with that. I think this picture is a little bit, well, I know it's a little bit out of date. I know this was, I want to say 2017 this picture came out, but what you're looking at is an artist representation of our Milky Way. And you can see there the different kind of like colors and cones are where we found some different kind of groupings of these exoplanets. So you can see that orange little reddish cone there is this like Kepler field that you're seeing right here, this little patch right there. If we were to fly through that, that's actually like where we're looking in our galaxy. And so then if we looked kind of towards the center, you could see there's like a little string of a lot of planets that we found with the micro lensing technique that are all kind of towards the center of the galaxy. But really, outside of our own little galactic neighborhood, we really haven't found any planets yet. I mean, these planets are so far away, and they're even in our own galaxy. I don't know if it would, well, I don't like saying never, but it would be a long time before we're going to be able to find, a planet in like Andromeda or something like that. The technology is nowhere near that point yet.
Yeah. And you have to remember that we've really only found the first exoplanet in the 90s. So we've only been looking for, Well, gosh, I hate to think that's been 30 years now. That makes me old.
Woo!
But yeah, so we've only been looking for, we've only known that there are exoplanets out there for sure for like 30 years. So we haven't even been looking all that long. And you may remember from that chart we showed you at the beginning how there was, you know, a couple up until we launched Kepler. And then there was a big spike. And then there was only a couple. And then TESS came along and there was another big spike. So it took us a really long time to even get good at finding these exoplanets. Now that we're better at it, hopefully technology will kind of increase at a maybe exponential rate and we'll start finding more and more and more, especially as we get better and better technology. But that's where we're at for now. Great question.
Definitely a big growing field.
Mm-hmm. Let's see. We've got one from Javier here who wants to know how black holes form. That is a great question too. Black holes are formed when a big giant star dies. So stars have life cycles, just like people and animals and plants and things. They're born, they live, they grow, they die. Now, it takes a really long time, millions or billions of years, but eventually a star will run out of fuel to burn, and that's when it will die. Now, black holes happen when, it's a really, really big star, the biggest stars that are out there. They die in this very violent thing called a supernova, which, without getting too complicated, it's basically a giant explosion. So the star gets to the end of its life and it blows up, and all of the material that was inside or around the star gets flung off into space, which is like that Crab Nebula that we showed you earlier. That's a great picture of a supernova remnant. But it doesn't destroy everything. So most of the material in the star does get blown off into space and make these really pretty pictures. But what remains at the very center is the very core of the star. So there is some material that is left over and crammed all the way into the middle. Now, a lot of times this will make something called a neutron star, which is just a very dense stellar core. But for really, really, really big stars, that will form a black hole. Because all of that stuff that was inside the star, because that star was so big and so massive, the stuff at the very center was so crushed under gravity and pressure that it got smushed together so tightly that it forms that black hole. And so the black hole is just the really dense, really strong gravity left over in the core of that dead star. It's pretty amazing when you think about it. Great questions. Let's see, do we have any others? Oh, we did have a couple more coming in. Excellent. What is a light year? That's an excellent question, Jonathan. A light year is the distance that light travels in a year. That's pretty much it. So light is very, very fast. It is not instantaneous. It actually takes time for light to travel. It's the fastest thing there is. You can't go any faster than light, but it does take time. So a light year is the amount of time that it takes for light, the distance that light travels in a year. That's it. So it's just another way that we measure the distance to things. Let's see, what else do we have? Mr. McFarland is asking, when searching for exoplanets, are there intervening streams of galactic material that interfere with distant object viewing? Dust, gas, spiral arms, absolutely. That is a thing that that always gets in the way. Pretty much any time that we're looking through the plane of our galaxy, that, you know, all of the material that's in between us and the very center, you can see, like the picture that Jeremy's got up, you can see it's kind of really dark in the center. So that's our galactic plane. And yes, that dust and gas and stuff does get in the way. This is another really great reason for us to use infrared instead of the visible light, because the infrared light can penetrate that gas and dust in a lot of cases. So this would be something that I don't know if direct imaging would be really great for it if they're super far away, but it might help. So we can look at it with different wavelengths and things like that. That's another thing James Webb's going to be really great for. It can look into the infrared and the UV just on either side of the visible spectrum. So that's going to be really cool. But yeah, it's always an issue that we're having to contend with for sure. Let's see, do we have any others that came in? I see someone, no name, is asking what my favorite planet is. Ooh, I like that question. I don't know, it changes sometimes, but I think overall my favorite planet is probably Jupiter. I think Jupiter is super cool, not just because it's really big, that is super cool, but it's also got tons and tons of moons, and I love moons, so the more moons, the better, if you ask me. And they're all really interesting and really fun to study. And, you know, Jupiter's like the king of the planets. So I love Jupiter. I think Jupiter's really awesome. What about you, Jeremy? What's your favorite planet?
You have such a solar-centric view, Tara. No, if we were talking about our own solar system, my favorite planet would be Earth, because I love the Earth. But
Earth is all right.
No, I'm really interested in Mars. I did research on the Martian atmosphere for a couple of years, and I was really interested in that and the geology, and just trying to think of like what happened at Mars to make it, you know, the way it is now I find it really interesting. But also like the outer planets, I feel like are like the planets that people aren't studying as much, I feel like are some of the most interesting, because like Neptune and Uranus and even Venus, like we have very kind of elementary understandings of, mainly because it's like they're either too far away, or in the case of the outer planets, or it's, you know, like we're not going to really, we don't have, it's, we'd rather go to Mars than Venus, because we know we can figure out Mars a little bit better than Venus. They're both pretty hostile, but you know, Venus is the crushing atmosphere, and the heat is, you know, and the pressure. It's not a place you want to really send a multi-million-dollar spacecraft. Yeah.
Not so much.
So yeah, I like some of those outer planets. My favorite exoplanet, I don't know. Might have to watch the video from last week. There's a video, or there's a planet that is thought that has a cycle with rock and lava similar to our rain cycle, where it's actually so close to the planet's so close to its star and it's tidally locked. One side heats up to crazy high temperatures. The lava on the planet basically evaporates like rain, or like water on Earth evaporates, is carried on to the dark side, and then, you know, falls like lava rain. So I'm not going to tell you the name of that planet. You're going to have to go either do some research or look in the last week's video to find it out. But that might be my favorite exoplanet, because it's just crazy. I don't know.
That is super cool. I don't know if I have a favorite exoplanet. I have a friend that studies these exoplanets called super puffs, which I think are really cool. These are planets that are huge, but really airy. They're about the density of cotton candy. So you can imagine like a planet the size of Jupiter that's made out of cotton candy. And so these are really big planets, and they have super puffy atmospheres, so they're not very dense. And I think those are pretty cool. Those are super neat.
That is awesome.
Yeah. All right, we had a couple more questions, 2 more coming in that I'm going to address, and then we're going to call it a day. Because Jonathan, again, wants to know about the size and the age of the universe. And this is an excellent question. From what we can tell, preface it that way, from our best, from what we can tell, the universe is huge, and really measuring the size and the age kind of go together, because at the scales of the universe, the best we can do is measure it in light years. So we can tell how far light probably traveled within a certain amount of time. So if you're talking about the age and the size of the universe, we usually put those things together, and we say it's about 14.5 billion years old, or 14.5 billion light years wide. Because we're seeing light that's traveled from things that are about 14 billion light years away. That's how long it took that light to get to us. So that's as far as we can see at this point. Once you get out past that, there's other stuff that gets super complicated, and then we don't know what's beyond that. But from what we can tell, 14.5 billion years is both the age and the size of the universe. Things get complicated when you start talking on those really big scales.
Yeah. And
I
to
do
try
planets
to,
and rocks.
yeah. We'll try to put that in like perspective for you because I struggle with numbers that big. So if we look at this Kepler field that which we were flying through here, the edge, so the far left where those purple planets or those purple dots that represent planets that are further away from the Earth, where that is located, I want to say is like maybe Emily or Tara can correct me or someone correct me if I'm wrong. I want to say like 4,000 to 5,000 light years away. And our Milky Way galaxy, so remember that the sun is back at the center of the cone here. We'll zoom out. Our Milky Way galaxy is at the low end 100,000 light years across. So that means that those planets are literally just right in our own little neck of the woods. And you can see as we're zooming further and further out, this massive cone, which didn't even look like a cone when we were at Earth, is now, getting really, really small when we even are just looking at our own Milky Way. And this is just a very, very small part of the universe. So it's big.
It's big.
It's very, very big.
Yeah, it gets really hard to think on those sorts of scales. That's why scientists that do that, what we call cosmology, have to think really, really big all the time. So it's pretty crazy.
Great question.
Great questions, you guys. All right, we are way over time, so we are out of time for today. But thank you again so much for bringing all of these great questions for us. If you have any that we didn't get to, go ahead and put them in the chat or a comment or drop them in our form. We'll try to either address them next week or we'll get back to you with the answers as soon as we can on those. But definitely be sure to come back next week. We're going to be talking about more cool exoplanet stuff, including what the future holds for our exoplanet studies and discoveries and what we think is coming next. Also, be sure to come back after that. That'll be our last exoplanets. And then in March, we're going to be talking about water in our solar system, which is one of my specialties. And I'm super excited to tell you guys all about water and missions that are going to look for water. And Jeremy will be stoked that a lot of this has to do with the very far reaches of the outer solar system.
Woohoo!
So we're all super excited about that. So also don't forget to like and subscribe and share and do whatever you need to do so you don't miss any of our upcoming Dome to Home episodes. Of course, all the old ones are still available on YouTube and you can share with your friends and family and whoever else you think needs to learn about this cool space stuff. Otherwise, hopefully we will see you again next week, next Wednesday at 3 o'clock Mountain Time. Hope to see you then.
Yep, same time, same place. Take care until then, everybody.